Imagine you are preparing a valuable dataset for your machine learning model. You have meticulously collected and cleaned it, but what if there are still some extreme data points lurking within your features, silently distorting your analysis and potentially misleading your model? When faced with these challenging extreme values, often called outliers, normalization techniques like the robust scaler are your most effective defense. In contrast, commonly used methods such as the standard scaler and the min-max scaler are generally quite sensitive to the presence of outliers. The crucial distinction between these techniques lies in the specific statistical measures they employ for their calculations. The standard scaler transforms data so it has a mean of 0 and a standard deviation of 1. However, both the mean and the standard deviation are highly susceptible to the influence of extreme values. Just one or two outliers can significantly shift the calculated mean and dramatically inflate the standard deviation, thereby distorting the perceived spread and central tendency of the entire dataset. Similarly, the min-max scaler, which maps data to a predetermined range like 0 to 1, relies entirely on the absolute minimum and maximum values observed in the dataset. If an outlier happens to be the true minimum or maximum, it will disproportionately expand the overall range, consequently compressing the vast majority of your typical data points into a very narrow segment of the new scaled range, making it difficult for your model to discern meaningful differences. Conversely, the robust scaler is designed to operate using the median and the interquartile range. The median is the central value in a sorted dataset and is inherently much less affected by outliers than the mean, representing a more stable measure of central tendency. The interquartile range, or IQR, specifically measures the spread of the middle 50% of your data. It is calculated as the difference between the 75th percentile and the 25th percentile. By anchoring its scaling on these robust statistics, the robust scaler effectively minimizes the impact of extreme data points, providing a transformation that more accurately reflects the typical distribution and variability of the bulk of your data. To effectively utilize the power of robust normalization, your initial step involves a careful examination to identify the presence of outliers and to determine their nature. Are they genuine, albeit unusual, observations, or are they simply errors in data collection? If your analysis confirms that these outliers are indeed valid data points that should be retained, or if you simply choose not to remove them for other reasons, then applying a robust scaler becomes an exceptionally prudent choice. This technique ensures that these extreme values do not exert an undue influence on your model's learning algorithm, allowing it to focus on the more representative patterns within your data. For example, when working with financial datasets that might contain a few extremely high-value transactions, the robust scaler will scale the data appropriately without letting those exceptional transactions unfairly shrink the effective range for all other, more common transactions. Grasping the underlying statistical robustness of measures like the median and the interquartile range is more than just technical knowledge. It empowers you to make truly informed decisions during your data preprocessing pipeline. This capability goes beyond mere data scaling. It is about judiciously preserving the authentic relationships and inherent structures within your data, even when confronted with unusual observations. Ultimately, adopting such robust preprocessing techniques allows your machine learning models to achieve faster convergence during training and produce more accurate, reliable, and generalizable predictions, precisely by guiding them to learn from the typical patterns rather than being sidetracked by statistical anomalies. By thoughtfully choosing normalization methods that specifically resist the adverse effects of outlier influence, you are directly contributing to the enhanced stability and superior predictive capabilities of your machine learning models. This diligent and informed consideration of your data's unique characteristics, especially regarding the nuanced presence of outliers, represents a foundational and indispensable practice that underpins the development of truly reliable and highly effective machine learning systems.